We will continue the optimality proof of the farthest-in-future cache replacement algorithm. Now next case we consider, we call it 3D. So in this case we have request to F. Request to F and S evicts X and S evicts some X which is not equal to E. So here what S prime will do, S prime does the same. S prime evicts the same element X. Since X is not equal to, we have a request to F and S evicts X which is not equal to E. So this X is also present in the cache of S prime. S prime does the same, it evicts X. And so if we compare the cache, so S prime evicts X and gets E and gets E. So we compare the cache of both S as well as S prime. So here we have cache for S. For S, what has happened is there is a request to F and it evicts X. So F will come in and E is already there in S. So now both E and F are there. This is for S, and for S prime, so S prime already has F, and in place of X E comes, so we get EF. Now caches are same. So just notice that this here both have the same cache, but S prime is not reduced because on request to F, S prime already have F. So actually there is no need to, this is a cache hit. So for S prime it is actually originally a cache hit. For this it was cache miss. But in spite of cache hit, S prime will evict X and get back E, so that both have the same cache. So now both have same cache, but S prime is not reduced. Just observe that S prime is not in reduced form. So next what we can do is, better I should relabel it as S double prime, because S prime is the final schedule. So it is not reduced. Now what we do is just make it reduced. Make S double prime reduced to get for S prime. So now both S prime and S have same cache. S and S prime have same cache. And also if we compare the number of miss, S prime has number of miss of S prime is at most number of miss of S double prime. And also the way we are making, so for S prime it is simply emulating S. So due to this emulation they will have identical cache miss. So if we compare, we observe that we can make this as cache miss of S. So this is case 3D. 3D, S prime is catching the cache and also its performance is not worse, it may be better. Now there are two more cases. 3E case we consider. So once again we have a request to F. Request to F and S evicts and S evicts E. Now we can compare both the stacks or the caches of S and S prime. So for S, what will happen? It has replaced, so S has E, it is replaced with F. So here we have cache miss, and for S prime it has nothing to do, it has a cache hit. So now once again S and S prime they have same cache, and once again our observation is that misses of cache miss, if we compare, it is at most cache miss of S. Now final possibility is not possible, 3F if we consider. This is simply not possible because the way farthest-in-future algorithm works, whatever request to E, it is not possible. So we write request to E is not possible. So its reason is very simple. Just observe that how this farthest-in-future algorithm works. So if we consider SFF, farthest-in-future algorithm, it evicts E in spite of F. So just remember our SFF and also S prime, they have evicted E because E is farthest in future. So and already F was also there. So it means first we'll have request for F, only then request for E will come. So actually this case will not happen. Why? Because up to this request of F, we have observed in the previous two cases that both S and S prime will have the same cache and S prime will keep emulating S. So we need not consider this case E. So E will come, then whatever S does, S prime will do the same, and both have the same cache. So we have seen in all possibilities, number of misses of S prime is at most number of misses of S, and also that S prime agrees with SFF, farthest in future algorithm, up to G plus 1 items. So this completes the optimality proof, as I have explained earlier. Now we'll apply the same algorithm to the LRU algorithm and see how it can be converted into the farthest in future algorithm using the same ideas. So once again, we compare both the algorithms, the LRU algorithm and farthest in future algorithm, and how we can convert LRU back to farthest in future algorithm using these exchange arguments. So we have to compare the both. So we compare farthest in future algorithm with the LRU algorithm, and we'll convert the LRU algorithm back into farthest in future algorithm. So this is farthest in future algorithm, and this is LRU algorithm. So now we compare the two and see where we have the difference and apply our exchange argument to convert it back. So we observe the LRU algorithm. First two steps, so both have the same input and with same initial cache. So for cache miss, cache hit, they perform identically. We need only to consider this cache miss. So first cache miss in LRU is CB CAB. C replaces A. We consider this in FF algorithm. CB CAB. CB CAB. In FF, C is replacing A. Here also C is replacing A. So it is working identically. So next two steps again are cache hit. Now here we get cache miss. So A replaces B in LRU. If we consider FF, AB in FF, A replaces C. So here we have a difference. So now we apply our transformation. So using our notation, the two algorithms are identically up to jth step. So this is our jth step. CAB. So here also in LRU CAB, this is our jth step, and after that we have J plus first step. J plus first step, and there also AB, this is J plus first step. So now we we compare with our definition. The FF algorithm is replace, so here A is replacing C. So we compare with our definition what S prime does and what S does. So S is our algorithm, LRU. So here we S evicts F. S evicts F. So S evicts F. So B is our F. This is our F. And S prime evicts E. S prime evicts E. So C is our E. C is our E. So to convert S into S prime simply copies the move of SFF. Copy the move of SFF. So we change it to A replaces C in this algorithm. This will change. This will change to A replaces C. It becomes A, B, CB. We have a cache miss and A replaces C, so that it matches with FF algorithm. After this, the next step becomes B with AB. And this is our step J plus 2. J plus 2. And now compare it with J plus 2 step of FF algorithm. In our FF algorithm, J plus 2 step is J plus second step. So next we have this. Next is B. And what is B? B is our F. So next request is of B. Request to F. This is request to F. So next is request to F, and S evicts E. So this C is actually E. C is actually E. If we consider here, C is E. So our algorithm S is evicting E. E is evicted. So if we compare with our earlier various cases in the proof, so this is case 3E. 3E where S, so here we have request to F. Request to F and S evicts E. This is the case. So in this case we have analyzed, and so F comes in, E goes out. For S prime, it is cache hit because F is already there. So it saves one cache miss. So after this, both algorithms become identical. So here we can see B with AB. This is same thing as in FF, B with AB. So now both algorithms perform identically after this step. So we have converted our LRU into LRU to FF algorithm, and LRU had 3 cache misses. This has 1 less, 2. So this is the procedure we apply. Given any other schedule, by stepwise exchanges, we can convert any schedule into FF schedule such that it may become better, and in the process we get the optimal schedule. Now we find the time complexity of this algorithm. So for time complexity, we use our notation. Using efficient data structures, we can reduce the time complexity. So we have size of u is number of elements in the main memory is n, and m is size of data sequence. Size of data sequence. And we have k is equal to size of cache. Now we have to find time complexity of this algorithm, and this is a very simple algorithm, and we make use of efficient data structure. So once again I will explain this with the same FF algorithm, how to implement this efficiently using efficient data structures. So once again we consider this FF algorithm. So I will make the data structures and then we can analyze its time complexity. So here what we do is we make doubly linked list, an efficient data structure. So for each A, B and C we make a doubly linked list. So we initialize the linked list with null initially, like this. We have A, B and C. Next we scan. We scan the sequence from left to right. We start with A. So every letter has some position like this: 1, 2, 3, 4, 5, 6, 7. So we'll record this. So each time we get a letter, we add its position in the linked list, scanning from left to right. So starting with A, first occurrence of A is 1. Store it like this. Second we have, next is B, position is 2. Position is 2. Next we have C, its position is 3. Next we have is B. Next we have is B, its position is 4. So we can keep the pointer at the rightmost node in the doubly linked list so that we can efficiently add the nodes. So next node to be added is 4. Next is C with position 5. 5. A with position 6. A with position 6. Then finally B with position 7. 7. So this will simplify our time complexity. It will reduce our time complexity. So first time we scan and do like this. Then for cache also we make a linked list like something like this. The pointers. So initially we have A and B, so pointing to A and B like this, A and B. So this is very efficient data structure. So now what is time complexity of this creation? So we have to account for this and this complete. So cache size is k. Number of alphabets is size of u, and size of u we have taken is size of u is n. Size of u is n. Data sequence size is m. Size of cache is k. So n and m. N and m. N. So k plus n plus m. So one complete scan will take time m. Initializing a, b, c will take time n. Initializing the cache will take time k. So this is initialization step plus. Now again we run the algorithm. So first we have a. So a we can check. We have to check these pointers, and so we can check the pointers. How much time it will take is k. K time to check the pointers. So we can know by checking the pointers if we have a hit or a miss. So in our case we have a hit. So hit, no, there is no work to be done. Second step. So this is the effort taken in first step plus second step also same. We have a cache hit. Next step we consider. So here we have a cache miss here. So it takes time k to know that we have a cache miss. Now we have to identify which one of A or B we have to evict. So once we know this, that we have only A and B, so we have to evict. Now we can identify A and B. So we have the timestamps A. So one more thing we should do, that we have to update this linked list. So for example, in the first step, when there is a cache hit, so we should remove this node. So we have to do this work also. So we remove this. So this will some more steps, and for simplicity we can write its complexity f big O of k, time proportional in k. So second step also we have to update so that we know the latest values. Now third step, we have to identify out of A and B. So the larger value is of A. So C evicts A. C evicts A. So A is evicted, and we change this pointer to C. So now the updated data structures will be something like this. A, in future 6 will come, 6, and then B with 4, B with 4 and 7, 4 and 7, and C. So C we will update this. We have to remove C with 5. And update our pointer. Now we have after this C and B. C and B. So this way we continue. So now we can observe that the time complexity at each step is big O of k. Only proportional to k operations we are doing, we have to check for the cache, and we can update it in constant time. So big O of k is the time complexity of each step, and these steps are performed m number of times. So now we can write our time complexity, k plus n plus m. So time complexity will be k plus n plus m plus m multiplied by big O of k. This is equal to k plus n plus m plus big O of mk. So these terms k and m, they are covered by big O of mk. We get this as n plus big O of mk. This is time complexity of our algorithm, farthest in future algorithm. And this is very efficient, assuming that cache size is small. It is only linear. So now we can also see the three characteristics of our greedy algorithm in the farthest in future algorithm. So the three characteristics are, first is the greedy choice property. So greedy choice property means local minimum implies global minimum. Local optimum implies global optimum. So here the rule is simply select farthest in future memory data element to be evicted, and we have proved that it leads to the globally optimal solution. This is first characteristic. Second is we incrementally build the solution, and third is we get a single sub problem. So we can easily see our single sub problems. So this is our original problem, it leads to a smaller sub problem, and so on, it continues like this. Now for incrementally building the solution, how we write our solution, we have to identify a notation, then we can easily see how we are incrementally building our solution. So at each step we can write as a solution which element to evict. So there are two possibilities. First, no eviction when there is a cache hit, and eviction when there is a cache miss. So no eviction we can write, keep it as blank like this. Eviction we can write the letter A, B, C, whatever. So this way we can continue writing our solution. So in this format, before starting our algorithm, our solution is empty. After first step, our partial solution is cache hit. So we can write our solution like this. Then again we continue, cache hit, cache hit. First two times we have cache hit, A and B. Next we have a cache miss. So we evict C, we evict A. So we can write our partial solution as like this, and so on, we continue like this. So we are incrementally building our solution, and before solving the solution we know what is our partial solution.